Hey everybody, this is my first tutorial on Redshift renderer for Cinema4D, so if at the end you have any sorts of comments, suggestions, or questions, I will go ahead and do my best to address those. I'll specifically be talking about a few of the nodes within the shader graph, which I consider essential to creating any sort of complex shader networks. And even though I'll be using Cinema4D during this demonstration, you can find these same nodes across all your 3D rendering packages using Redshift with the same workflow and functionality. So before I jump into the nodes, I want to give you a quick tip which is considerably useful when working in the shader graph. Let's say I just want to view this specific texture here by itself without the material parameters. So what I can do is I can connect that to the surface on the output node. And now I'm just viewing this flat shaded color texture projected onto the UVs. Now, another way that you can connect this to the output is by selecting your desired texture or node, going to the tools and hitting connect node to output, and will automatically take that selection and connect it to your output, so you're viewing it here in your render view. Now, going to every single node and going to the tools and clicking connect node to output is going to become a hassle very quickly. So the cool thing you can do is actually set up a hotkey to trigger that command automatically. So I'm going to go ahead and pause my render view. I'm going to go to the toolbar at the top of Cinema4D here. I'm going to go to Windows, Customization, Customize Commands, and up here, if we look back at what this tool is called, it's Connect Node to Output. I can type in the name filter, Connect Node to Output, and you see that it's showing it right here. So I can select that. You want to make sure that you're selecting the shortcut here, so click that, then hit, in my case, Control-Shift-C. I can hit Assign, close this, go back to my shader graph. Now if I disconnect this, if I hit Control-Shift-C, you can see it's connecting my output to whatever node I have selected. If I turn on my IPR, put this in progressive mode for now so it's just faster to see, you can see that I can very quickly switch between all these nodes. So in complex shader networks, if you want to know exactly what's happening in a specific part of your node tree, you're going to be doing this all the time, switching to your output so you can see exactly what's happening, and it is incredibly useful. So the first node I want to talk about is the triplanar node. And we can find that by going to the Find Node search bar here in the shader graph and typing in triplanar. See, it pops up here underneath the utilities. I'm going to drag that into the shader graph. Now, whenever you apply a texture to a 3D model, that texture is going to be mapped onto the object's UVs. Each UV cell is essentially referencing a polygon on your 3D model. So whenever you apply an image over one of these UV cells, it will be reflected on the correlating polygon on your model. Now, the best part about the triplanar node is that it does not care about UVs, and instead uses spatial projections to map your textures onto your model. Now, we can quickly visualize how this is working by connecting our triplanar node to our output, starting the IPR, and the first thing you'll see is that your entire model will become red. And that's because by default, you have this option ticked on in the triplanar node, same image on each axis. So if we uncheck that, now you'll see these three different colors, red, green, and blue. And what's happening here is that all three of these colors are being projected on their respective positive and negative axes onto your model. While many projection mapping techniques result in issues such as hard seams or texture stretching, the triplanar node has two options which help alleviate that issue. If we take a look at this blend amount parameter, as we begin to increase this value, you'll notice that these axial projections begin to blend and overlap together, effectively hiding any seams. And secondarily, if we come down to this blend curve parameter and begin to increase this value, you can see that it begins to tighten up that overlap. So before we jump into the rest of these parameters here, let's go ahead and replace all of our solid colors with some actual image textures by piping these three image textures into the respective axes. And immediately you can see all of these image textures mapped onto the object here, and we can go ahead and dial in whatever kind of blending we see fit, effectively eliminating any visual seams. In most practical applications, you're going to be mapping the same texture on all axes. So we can reactivate that by going back to the same image on each axis parameter and checking that. And now we're using whichever image was piped into the image X of the triplanar node. So I can go ahead and delete these other two texture nodes now that we're just using this singular image. At the moment, the scale of my texture is much too large for my model. So I could go into my texture node itself and begin to increase the scale to shrink that down, or I can go into the triplanar node and begin to adjust these scale values. And I can increase the scale values per axis to get the same result. I could also set individual values here to create non-uniform scaling, but as you'll see, we get this stretching as a result of that. So I'm going to go ahead and reset these back to 0.1. Next, we have the offset parameter, which will allow us to shift our texture along the respective axes, followed by rotation, so we can rotate our texture per axis. And finally, we have the most important parameter, especially when it comes to animation and deformation, which is the projection space type. Now, by default, this is set to object mode, but to better visually understand what's happening here, let's go ahead and switch it over to world mode. And I'm going to go ahead and go over to my viewport here. Now, pay attention to what happens in the render viewport as I manipulate the sphere. So as I move this, you can see that our texture is not actually being influenced by the transformation of our sphere, and we're getting this swimming effect. The same thing goes for any sort of scaling or rotation, especially apparent when I'm rotating it because you don't see the texture moving whatsoever. So if I go ahead and go back here and switch this back to the default of object mode, and once again begin to apply these transformations to the sphere, now you're seeing that whenever I scale, rotate, or move the sphere, our texture is sticking to the object. This leaves our final projection space type, reference mode. Now, reference mode deals directly with any sort of deformation or displacement. So if I go to this displace deformer here and activate it, you can see that I'm deforming my model, and my texture is stretching along with the deformation. Now, if I were to go back and switch this to object mode, now our triplanar node is projecting the texture as if this deformation was the default state of our model. And because of this, any sort of animation within our deformation will cause the same texture swimming as we observed previously in world mode. So if we switch this back to reference mode, our texture will now stretch along with the deformation. This brings me to another useful tip. As we saw previously, the triplanar node has this coordinate dropdown which contains vector data, which allows us to influence things like the scale, offset, and rotation along each axis. Now, let's say that you had a completed material with multiple triplanar nodes, and you wanted to uniformly adjust the scale of all of those nodes at the same time, or you wanted to create a uniform scale for an individual node so that you didn't have to go through here and type each one out manually, for example. In this case, you can see that it would take me a long time if I had a very complex network to go through and dial in exact values of each individual node. So what we can do that's really useful is go to the math drop down here. So in the example that we want uniform scale, so we don't have to type each individual axis to the same number, we can use this constant node, and we can connect that here to the triplanar coordinates scale. You can see this has been overridden and is now being controlled by the constant. If I set this to a value of 0.01 and click back on the node, you can see, well, it doesn't actually show that, but you can see in the viewport that if I increase this, I'm controlling this shader scale uniformly on each axis. Furthermore, if I want to control both of these triplanar nodes at the same time, I just connect this same node to the coordinate scale here as well. And now I'm influencing both of these triplanar projections at the same time, so I can adjust the scale uniformly. You can do that for every single one of these parameters. So if I wanted a separate one for rotation, I could hit the rotation here on each of these and type in my value that I want to use, let's say 45 degrees. And you can see that I am uniformly adjusting both of these triplanar projections. Now, in the case that I wanted to set values for each individual axis, I would use the same constant node, except I would go to the constant node and change it from a real data type to a vector data type. And now you can see that we have 3 values for each axis, and I can type in a value here. So if I set them all to be uniform, we're back where we started, but now I can set individual values. And you can see, since I have this plugged into the scale of the triplanar nodes, it is affecting the scale non-uniformly based on these values along each axis. Next, I'd like to cover some color correction and remapping nodes. So we'll go ahead and start with the most basic one, which is the, you guessed it, color correct node. Go ahead and search that here and drop it in my shader graph. Connect up my texture to the input and the output to my shader diffuse color. Start up the IPR. Now, if you take a look inside of the color correct parameters, it's going to be very similar to parameters that you might find in After Effects or Photoshop, for example. You've got the gamma. As I increase that, it's going to brighten my texture here. If I lower it, it's going to have the opposite effect of darkening it. Contrast here, the higher it goes, the more contrast I'm going to be adding. The lower it goes, I'm going to be reducing that contrast. Hue shift, it's basically going to be pushing the colors along that spectrum, similar to any hue shift that you would find in other programs. So as you see, as I push it along, I'm shifting that hue along the spectrum. Saturation scale, again, you guessed it, if I raise this number, it's going to increase saturation. If I decrease this number, it is going to reduce it. A value of 0 makes it completely grayscale. And once again, levels, if I increase this, I'm going to be brightening. And if I decrease this, I'm going to be darkening. The value of 0 makes it completely black. And the use HSV conversion tick box means that we'll be using hue saturation value calculations to deal with our parameters here, whereas if we uncheck it, we'll be using RGB. And you can demonstrate the different results here by upping the saturation scale to something like 3, for example. You can see we have a very saturated color now in our texture, and if I switch it to HSV, it's going to yield something a little bit different. So while the color correct node has its obvious uses, I rarely find myself using it for anything other than color correcting the diffuse input, which brings me to my next set of nodes, which will start with the ramp node. So I'll go ahead and search up the ramp node here, see it here under textures, drag that guy in. I'm going to go ahead and wipe out my color correct node. So bringing back my simple sphere here, I'm going to go ahead and take my ramp node and plug it directly into my output so we can observe how it works. And what we got going on inside here is a very simple gradient ramp, and we can kind of see how that's being mapped onto our sphere as I adjust this ramp here, and you can see that I'm shifting that gradient along the UVs of my sphere. And we've got a few options here. We've got some different mapping types. So currently we're using vertical mapping. If I switch this to horizontal, you'll see it flips to the horizontal. We've got diagonal, radial, circular. See that point there. And all of these function as you would presume they would, and if you've ever had any experience using any sort of gradient ramp. And we can move these points along as we please. We can add color to them if we'd like. We can add multiple points, multiple colors. And so now you can quickly understand here this visual, just exactly how this is working, right? So we got a lot of options here. And then if we'd like, we could add noise to break up the gradient a little bit. So if I add a small number here, say like 0.01, you can see it start to get a little bit wiggly. Maybe something like 0.1 will be more visible. You see, breaking up that gradient here with a little bit of noise. You got different frequencies if you want to adjust the scale of the noise. So the lower you go, the bigger it gets. And the bigger it gets, or the bigger the number is, the more fine the noise becomes. So now that we've established the basic parameters of the ramp node, I'd like to jump up here to the source parameter, which is going to open up a new door for us when it comes to using this node. So by default, it's set to auto mode, which means it's going to automatically determine whether it uses UV map mode or alt mode. So you really only have two modes here. Auto is just going to determine it for you. So if I switch this to UV map mode, you're not going to see any visual difference going on here on our model. And that's because the UV map mode is as to be expected. We're mapping the gradient ramp onto the UVs of our model. However, when I switch this to alt mode, you're going to see that our mesh becomes entirely black. And the reason for that is that alt mode is meant to be used with a file texture. So if I take my texture here and I pipe that into the input of the ramp, well, it is set to alt mode, you're going to see that it has been converted to a grayscale image. Now, if I switch this back to UV map mode, it's going to override it with the gradient ramp, and now we're just laying the gradient ramp onto the UVs. But once again, if I set it to auto mode, it's going to automatically know that there's a file texture being piped in and use alt mode. So first off, if I once again switch to these different mapping types, which we saw generated different kinds of gradients earlier, you're not actually going to see any difference. And that's because the actual mapping type is using this triplanar to project the texture on, and the gradient itself is ignoring this mapping parameter because instead it is now acting more like a colorizer than an actual physical gradient. And we can observe that if I take this slider here on the black and I push it closer to the midtone, you're going to see that I'm actually darkening all the darkest values on my texture. And likewise, if I slide my white slider here over to the left, closer to the midtones, you can see I'm now brightening up all my brightest values on the texture till I get it to pure white. So it's colorizing it. And if you're not entirely sure what I mean by colorizing, if I actually just change this white value to an actual color, red, and I change this dark value here to a blue, and I once again slide this, you see that I am actually replacing the darkest values on this texture with the color blue and the lightest values with the color red, and everything in between those midtones is using this gradient interpolation. Additionally, I can add as many of these little color droppers as I like. So if I put a green in here and I adjust things here to line up with my values, see, I'm getting 3 colors acting on my original texture. And from here, I can save a preset. I can load presets, drop this rainbow in here, for example. But what's most important to understand, and I can demonstrate that here if I go and reset my ramp, that this colorizing effect is working off of a correlating value on the original texture itself. So you see, even though in my ramp here, we have a completely 100% black and a completely 100% white, if we look at the output of our remapped texture here, we don't actually see anything on this texture that is 100% black or 100% white. So in order to have these values actually translate, as maybe we like something to be definitely 100% white, we have to slide it along those values of the original texture until we're actually replacing one of those values. And you see I really got to push the white pretty far, and now I'm starting to get things that are 100% white. And for the black, do the same thing. And if you'd actually want to see what the pixel values are themselves, then you can just open up your options here and just cursor over, and you're going to see the values popping up here to the right underneath the pixel display and RGBA here. So now you see we're getting closer to a value of 0 within the blacks and closer to a value of 1 in the whites. As far as practical uses of this ramp node, we probably would not be using it in the diffuse channel, as that's the color channel. So I'm going to go ahead and pipe in my colored texture here before the remap into the diffuse color of my shader. Pipe that into my output. what we can use this ramp node for is to help us create variation in something like the roughness channel. So if I go ahead and take my ramp node, drop that guy into the reflection roughness, and give this some reflection here. Just go ahead and max that out. No, we're not creating a realistic material. So by default, I'm actually going to disconnect this so we can demonstrate. So at a value of 0 in roughness, we have 100% reflection. And at a value of 1, or as we push it up to 1, you can see that we're creating 100% roughness, whereas the reflections are getting extremely blurry to the point where it's almost diffuse. So to create a connection between this numerical value, which we can easily understand, and compare it to the ramp, let's go ahead and connect the ramp directly back into the reflection roughness once again. And instead of having this gradation, let's go ahead and start with a solid color. So I'm going to set this complete black. And if we compare our result here, you can see that we actually are getting a roughness, something similar to a roughness value of 0 because we're getting 100% reflection. So likewise, if I begin to bump this up, so go ahead and start with 50%, you can see that our reflections are starting to become rougher. And as I set this to 100% white, now we are getting something that is 100% rough. So you can essentially think of any sort of black value as giving that a numerical value of 0, and a white value a numerical value of 1. And everything in between is going to be interpolated between those two numbers. So this brings us to a quick gotcha moment, which I'd like to clear up without going into too much detail, because this stuff can get a little confusing. So the way I'm going to demonstrate this is I'm going to go ahead and disconnect everything from my material. I'm going to clear out the reflections and just leave it at a default diffuse 50% gray. I'm going to go ahead and put in a value of 0.5 for my weight. So since we can understand that a value of black here translates to a value of 0 numerically, and a value of white translates to a value of 1 numerically, we could assume that we could replace this weight value of 0.5 by setting this to something like 50%, right? And plugging that guy into our material, diffuse weight. But suddenly we're getting something that yields a much darker result. So I'm going to go ahead and set this to bucket and save out a few snapshots so I can make some comparisons here. So this is our ramp at 50% gray, which we would assume would translate to a value of 0.5, right, if we have a good understanding of how numbers work, right? So I'm going to disconnect that. And let's get a render here of our default weight at a value of 0.5. Okay, I'm going to save that. Snapshot. Okay, so clearly there's something going on here that doesn't make sense to us. And I'm going to take a constant, and I'm going to set it to a value of 0.5. And okay, since that's a actual numerical value, I'm going to plug that into the diffuse weight. See what we get here. Okay, I'm going to save a snapshot of this guy here. I'm going to compare these two, and these two are working as I would presume, right? So why are we getting a darker value here from the ramp color at 50% than we are with numerical values? And the reason for this difference here has to do with sRGB and linear curves. So these numerical values are using linear math, and this ramp node is using an sRGB gradient. So in order to convert our sRGB gradient to a linear gradient, I'm going to go ahead and bring in a color correct node. I'm going to pipe in our ramp node to the input. Then I'm going to connect that now to the diffuse weight. And we're not going to see anything happening here because we haven't made any complete changes here. But what I'm going to do is I'm going to go to the gamma in this color correct, and I'm going to set it to a value of 2.2. And now we've converted that sRGB curve to a linear curve so that we can get a predictable value. So now our value of 50% is going to align with our numerical linear value of 50%. And if I take a snapshot here and compare it now, you see that we're getting the same predictable result. So if you were ultimately trying to translate your ramp gradient value here into an actual numerical value, then this is the step that you would need to take. So let's go ahead and jump back into understanding how we can use this ramp node to manipulate our texture. And I'm going to go ahead and connect my color correct node back to the output, which once again is not entirely necessary unless you're trying to get predictable numerical results. And I'm going to go ahead and look at my ramp here once more. I'm going to go ahead and add in a black value and a white value. And I'm going to go ahead and start sliding these around until we get some nice contrast going on here in our texture. It's too much black. I can also adjust this interpolation point here. I can also type in actual numbers here if I'd like, as well as changing the overall interpolation from smooth to cubic, linear, step, if you want a solid transition here. I'm going to reset that to smooth here. Now, once I've gotten to this particular stage, let's go ahead and plug this guy back into our materials roughness, reflection roughness output here. I'm going to go ahead and once again plug this guy directly back into the color without any sort of remapping on it. Expand this a bit. I'm going to wipe out the weight port now that we've finished with that guy. I'm going to reconnect our shader back to our output so we can see what's happening here. All right, so putting my reflection back up to 100% weight. Now that I've added contrast to my remap here, we can presume that the lighter values are going to result in blurrier reflections, and the darker values are going to result in more completely reflective areas. So just to make that extreme really quick, let's go ahead and bump this black value up here so we've got a nice balance between rough and reflective areas. And once again, viewing that, now we can clearly see these patches here. We've got a very patchy reflection where we've got these areas of 100% reflection. We've got areas of 100% roughness. So you can easily see how we can use this remap node to take a texture and put it into our reflection roughness to create a varied reflection. Now, let's say that we don't actually want any areas to be 100% reflective. Well, with our understanding that these values here are on the darkest end, or the black values are 0 and the white values are 1, we can go ahead and bump this black value here to convert all our darkest values to something that's a little bit closer to white. So let's start with 35% here. And it's always easier to see exactly what you're doing to the texture itself by directly viewing it. So let's say I actually want something a little bit closer to 25%, which once again, with this conversion, is going to translate to a value of 0.25 mathematically, right, in our roughness. And let's go ahead and take this white and say we don't want it to be 100% rough, but maybe something like 60. And now we've got a very, very slight kind of difference here, but it's enough to create that subtle detail. And if I'm not liking the contrast here, I can adjust these points to kind of spread that out a little bit. There we go, I'm liking that. And now if I plug that right back in, take a look at our overall result, you can see that we're getting something that at first glance looks fairly uniform. But if you get up close and you like render this out at 1080p, you're going to see some very, very, very subtle breakup, which is exactly what we're trying to achieve. And of course, I can also invert this gradient here if I want to reverse the effect. So I can change my darker values to remap them to a lighter value and remap my lighter values to a darker value. And once again, see what's actually being produced by this. Take a look here. So I'm going to kind of have to adjust the contrast here between those dark and light remapped values. Bring this guy back down. And now I've effectively inverted that effect on the texture. So the final two remap nodes I want to talk about can be found by searching range in the search bar here, and specifically we're going to be going over the change range and color change range. But let's start with the color change range because it's more similar to the ramp node. So I'm also going to bring in the ramp node so we can make a direct comparison between the two to help us better understand how the color change range is working. Because if we take a look at the UI here, it's drastically different and a little bit intimidating. Well, the ramp node is by far the most visually intuitive remap node that you'll end up working with here. So if we take a look here in the color change range node, you can see we start with the input parameter, which is going to be where you pipe in your actual texture. And then we have the old range min and old range max. Now you can think of the old range min and old range max similarly to moving the sliders along the gradient. So if I were to move my black slider closer to the midpoint and the white closer to the midpoint, it would be similar to increasing this value here, this black value, and decreasing this white value, right? So it's essentially like I'm using these values to move the points on that gradient, right? One important thing to note, however, is if we actually take a look here at our node and pipe in our texture first of all to both of these nodes, is that first off, we're retaining color with the color change range. We're not actually affecting the color. We're not colorizing our texture. We're only shifting the value. So if I go ahead and reset this to default, we're not going to see a difference here if we switch between the color change range and directly pipe it into our texture. And as I increase this value here in the old range min and max, you're going to see that we're getting contrast, but we're not actually affecting the color values themselves. Likewise, in the ramp node, resetting this back to its defaults, I can move these along to create contrast as well. But one thing you'll notice is that there isn't a direct correlation between the position percentage and the actual value that you set here. So you're going to have to kind of work those independently. Now, switching back to the color change range, let's take a look at the new range min and max. Now, you can think of the new range min and max here being similar to actually setting an exact value or color in your little knots, right? So if I set this darker knot in the ramp to red and the lighter knot to blue, then that would, let me take a look at that. Obviously, they're not going to be directly lining up in terms of the positions, as I talked about. But you can see we're getting that effect that we talked about earlier, where we're actually colorizing the brightest and darkest values. And if we switch back over to our color change range and do the same thing, I'm going to go and connect this to my output so we can see what's going on. If I set my range min to a red color and my range max to blue, you can see we're effectively getting the same colorizing. Once again, an important note here is that the same sRGB to linear conversion will be required if you're trying to get an exact numerical value for something like the weight or roughness. And we can demonstrate that by remapping our range min and max to a 50% gray value. So I'm going to set both of these to 50% gray. And if we take a look at saturation here, if we take a look here, you can see that we're getting that 50% gray. And if we plug that in to our diffuse weight, for as we did previously, turn this guy on here, plug that into the output, you can see that once again we're getting that darkened value. So in order to fix that, we're going to pipe in our color range into a color correct, set at a gamma of 2.2 to convert that sRGB curve to a linear curve and give us the predictable numerical value based on the actual percentage values here So if I set that to 50%, it would translate to a value of 0.5, right, once I converted it. And now if we switch between these, you can see that we're getting the result that we want. So for a final comparison between these two nodes, you can see that we can use the color change range similarly to that of the contrast parameter in the color correct node, as moving these sliders will result in contrast on the texture without actually converting it to a grayscale image. But as far as colorizing goes, you can see that compared to the ramp node, we're only limited to 2 colors. So the ramp node would be more effective at creating a complex gradation of your texture. And so for our final remap node, we have the change range. And if we pull that guy in here, you can see that now we're looking at something that uses complete numerical values rather than a color or gradient. So here we have the same exact parameters. We have an input, which is where we pipe in our actual texture. And we have an old range min, an old range max, a new range min, a new range max. And these old range and new range functionalities are identical in terms of how they influence the texture to that of the color change range. So we can think of our old range min and max as shifting those knots to create contrast. And if I go ahead and take a direct look here, as I increase my min value, you'll see that we're shifting the darkest values up towards the midpoint. And as I lower my range max, you can see that we're shifting the brightest points down towards the midpoint. Now, immediately you can notice that because of the difference in calculations between the linear numerical values and the sRGB color swatches and gradients, we're getting something that's a lot different in terms of predictability when it comes to adjusting these values. So I'm going to go ahead and take this down to something like a value of 0.06, and I'm going to set the max to something like 0.25. And now we're getting something a little bit more along the lines of what we were doing before in terms of getting a nice balance between the darkest and brightest values. So moving down to the new range min and max, you can think of these two parameters as being exactly the same as when we were changing the values on those knots on the ramp node, right? So we're actually remapping the values from the original values of pure 100% black and pure 100% white, if we got that contrast, of course, to something of our own choosing. In this case, because we're dealing with strictly numerical values, we don't have the ability to add color, but we are able to enter more precise numerical values, which we could, of course, use in any sort of parameter which deals strictly with those numerical inputs. So if I go to the new range max here, and I lower this value to, say, 0.7, I'm taking my original value, max value of 1, or 100% white, and I'm lowering that to 0.7. So the highest value that I'm going to get, depending, of course, on the contrast, is 0.7. And for the lowest value, I could do the same thing. So anything that is 100% black or has a value of 0, if I raise that to, say, 0.3, now the darkest points on my particular texture are going to have a value of 0.3. So this way, if I want to create some sort of variation, for example, say in my roughness channel, so I can go ahead and plug this guy back into my reflection roughness and pipe this guy back into the diffuse color. Once again, bring the reflection weight back up so we can see what's happening here. Okay. Now, if I set both of these to the same exact value to start, say I set them both to 0, then of course we're going to see 100% reflection. If I set them both to 1, we're going to see 100% roughness. And if I directly view my change range, you can see that a value of 1 is white and a value of 0 is black. So reconnecting here to my actual shader output, we can clamp our roughness values to a numerical value and get that same sort of variation, but with very precise numbers. So let's say, for example, that I was doing some testing and I liked a roughness of 0.3, but I wanted to get some nice variation here. So going back here so we can visually see the variation. Let's say I wanted my max value to be somewhere around 0.6. So now I'm getting some very, very subtle differences here to break up that overall reflection roughness intensity. And now we're getting that very, very subtle breakup in the reflective roughness here that we were trying to accomplish before. So next up, we have the color layer. I'm going to go ahead and grab that and drag it into my shader graph. Take a quick peek at the parameters here. So we've got a base layer, and we've got multiple layers, actually 7 additional layers, which we can blend it together and overlay on top. So I'm going to go ahead and pipe in my first image here into the base color. And I'm going to view that in my output. And you can see we're getting something completely black. And the reason for that is because by default, we have our layer 1 checked on, which is being essentially overlaid on top of our base layer. So you can see that it has a solid color of black. So if I were to change this to red, you would see that black become solid red. And if I turn it off, we're going to see our base layer. So you can think of this very similarly to a Photoshop layout, right? So if I enable my layer 1, and let's say I want to blend together these two images. So I have this kind of white cracked rock, and I have this very brown stone. If I take my white cracked rock, okay, I should have thought about that a little bit. And if I connect that to my layer 1 color input here, we're going to be seeing this white rock override the base layer in the same way that the solid color was, because we have this set to a normal mode. So if we look down here in the options, we do have a mask and a blend mode. So first of all, the mask essentially acts as the opacity channel of our image. So as I lower this to say 0.5, now we're giving this white rock a 50% opacity so that the base layer brown rock is beginning to bleed through. And as I lower that even further, you're going to see more and more of the base rock coming through, and a value of 0 is going to hide this layer 1 completely. Now additionally, I can use an actual black and white image or any image, which I can convert to a grayscale image, as a mask. So anything that is black, 100% black, will be completely opaque or transparent, and anything that is 100% white will be completely opaque. So let's go ahead and take this image here and add a little bit of contrast to it with a ramp node. So I'm going to pipe this image guy here into the ramp. I'm just going to switch it to alt mode. I'm going to go ahead and view the result of this ramp node. I'm going to bump up the contrast here by pushing the darker values up and bringing down the light values. So we're getting points of 100% black and 100% white, so we can really demonstrate this. Okay, and then I'm going to take this output and pipe it into my layer 1 mask. And if we now take a look here, you're going to see that the areas on this mask, which once again are white, so here we can see these white areas, that's where our white rock is now going to be showing through, right? So we've effectively blended these two images using this black and white mask. Now additionally, we can adjust the way that these two images blend together. So if I remove this mask, first of all, and I kind of begin to scroll through these blend modes, once again, completely the same as you would find in Photoshop in terms of functionality. Can add it on top, can subtract, multiply, difference. You have all of your basic modes here, overlay, and once again, you can either use the mask slider to adjust the overall kind of effect of that, or if you only want this particular image showing through in particular areas, you can actually combine the masked texture here with the blending mode. So now, once again, if I set this to normal, see that we only have it showing up in these particular areas, but we can still apply an additive effect or a multiplicative effect. It's only going to affect the base layer, however, in the masked areas. So we can really start to get some very interesting results by utilizing all of these layers. And even though we're limited to 7, we can always copy our color layer, pipe the output here into the base of a new one, and add additional layers on top of that. So you can essentially have an infinite number of layers if you so choose. All right, so next let's take a look at the curvature node. I'm going to go ahead and search that up and drop them in. I'm going to connect that directly to my output so we can see what's going on here. And immediately we see this very, very cool procedurally generated effect here. And we have two main modes. We have convex and concave. The curvature versions of these, I believe, are just older legacy versions. So we'll be using convex and concave primarily. So for convex, essentially any outward curvature on the mesh will receive a white value, and the opposite will receive a dark value or a value of black. So let's go ahead and reduce the radius on this so we can see a little bit more of a precise result. So I'll set something like 0.02. And now you see we've kind of clamped that to only the most qualifying convex parts of the mesh. And while we're still getting these areas of gray that maybe we want to eliminate, we'll get into that in a moment. So let's go ahead and switch this over to concave. And quite the opposite, any areas or any parts of the mesh which have these inward protrusions or grooves are receiving the same treatment of getting white mapped on to those areas, and all other areas which we would consider convex are getting a black value mapped to them. So then for the sample value, this, I believe, influences the accuracy of this procedural calculation. So in most cases, the default value is probably going to be good enough to serve all your purposes, but if you're experiencing any sort of strange artifacts or it's not working on certain parts of the mesh, then you could probably try to increase this value. And then we have the consider same object only. So when I have this checked off, it's going to treat this entire model as if it's one complete singular piece. But if I check this on, if I have any sub pieces to this model, as you can see, it's actually separated into multiple parts. It's going to treat each individual part independently. So if you had two chunks of the model that were very close together, creating some sort of concave or convex surface, or even intersecting each other, for example, then leaving this unchecked would take those parts of the model into account. So in most cases, you want to keep this unchecked if you're applying your material to a model that's made up of multiple components. Switching this guy back to convex, let's see how we can deal with these, clamping these somewhat gray values if maybe we want to get rid of them, or just add an overall contrast to this effect. So if I switch to the remap tab here, we've got a lot of options here, and there's a lot of different ways that you can go about doing this, but usually I like to go ahead and start with the bias and gain. So as I lower the bias value, you can see that we're actually pushing those gray values closer to a value of black, similar to like the remap nodes which we'd gone over previously. So now that I've lowered my bias here, you can see that I've completely clamped all those gray values to a value of black. And likewise, if I push this up in the opposite direction, I'm now pushing those gray values closer to white. And our gain value here is going to give us similar control as I move it upwards. We're darkening values, and as I move it down, we're brightening values. So if I wanted to get something more contrasted, I would start here. But if I wanted to actually break up these edges so that they're not so uniformly in width or shape, I could actually use a texture image like this to actually break up that curvature map. So once again, there's different techniques that I've seen for achieving this result. I'm going to go ahead and take a look back here at my curvature node. I'm going to take this texture image, black and white texture image, which I've piped through a remap node to add contrast, and I'm going to go ahead and input it into my remap contrast value. Now immediately you can see that we're breaking up those edges, but we also have a lot of spillage, and maybe this is something that we want, but we can actually hop right back into our bias and gain and begin to adjust that. So I can start bringing the bias down to push those gray values closer to black. And now we're eliminating a large majority of those gray values where otherwise, there would be spillage. And maybe I can adjust my gain a little bit to get the contrast dialed in even more. And now I've effectively taken that texture and used it to break up my curvature into something a little bit more organic and non-uniform. So this leaves us with a completely procedurally generated mask that we could use anywhere that we saw fit within our network. One important note is that the curvature node can't actually be used when it comes to building a custom displacement map or used in a network that influences the displacement map, as it is calculated after the displacement. Another really useful procedurally generated effect is the ambient occlusion node. So if I type in AO and drag this guy in here and connect him to my output, we can take a look at exactly what this does. Now you'll see right away that we're getting almost this sort of shadowing effect, but essentially what ambient occlusion does is it darkens up all the areas where two surfaces meet. So you can see these grooves are darkened, and really all areas where you have two objects within a specific distance of each other. Now, we got a few options here. Samples is going to adjust the quality, so the higher I take this, the less noisy the ambient occlusion will become. As you can see, there is a gradation from white to black, and then we have these two values for the bright and dark. So the occluded areas will be using black, and the non-occluded areas will be using white. So I could actually even hop in here and throw in a color. So I would put in a red for the bright areas and a blue for the dark areas. You can see exactly how that's working. So you get a nice kind of interesting, more artistic output if you put some colors in there. And then we have spread. And if I go ahead and start adjusting this value, if I bring this to 0, and then I bring it to 1, it's almost like a feathering effect. So at 0, we're getting a harsher transition where there's no sort of interpolation between the dark and bright values. And a value of 1 is going to be a much more gradual interpolation, and we see them blending very nicely here. Okay, so then if we set this back to 0 so we can move on to the fall off and see this a little bit more clearly, as we bring the fall off value up, we're essentially affecting the transition of intensity of the darker value. So you see at a certain point, we're kind of maxing that out, right? So if we set the spread up to 1, brought this back to 0, right? So a value of 0 on the fall off means we're completely removing the dark component. And as I begin to increase this, we're increasing that overall intensity of the dark value. And if I go ahead and drop my spread back down to 0, reset my fall off to say 1, the max distance is going to allow us to clamp this occlusion effect below this kind of maximum intensity point. So if I put in a value of 0.1, now you're going to see the occlusion only occurring in the areas with the smallest distance, right? So these very, very tight grooves. And if I begin to increase that, you'll start to see the effect expand to other parts of slightly higher distance, right? 5, 15, 25, until we get to a certain point where we've hit the maximum distance for occlusion. All right, and then furthermore, we can have reflectivity occlude. So any place that there's these kind of hot reflections, we're going to get occlusion in those reflections. We can invert our normal, which is essentially going to flip the effect here. So if I bring the max distance down a little bit, you can see when I turn it off, it's got your normal occlusion. When I flip it, it's inverting that occlusion, similar to the concave, convex functionality on the curvature node. Got different output modes. You can have occlusion in your alpha. Consider same object only works, once again, very, very similarly to that of the curvature node. If you check this on, if you have multiple components of your model, it is going to ignore all those areas where the two separate components meet, whereas if I uncheck it, it's going to treat it as a uniform, singular piece of geometry. So I'm going to go ahead and reset all of my parameters here. Going to bring up the spread so that we get some nice gradation here, some nice fall off on the edges so it's not so harsh. Going to adjust my max distance a little bit so I'm only getting the occluding effect where I'd like. In fact, maybe even go smaller, 0.5 for example. And now I essentially have generated another procedural map where I can use this as a mask to have certain effects or textures show through just these white occluded areas. I can also pipe that into a ramp in alt mode. So you can see I can really clamp down those white values if I want them to be a little bit more intense. And once again, I can use an actual texture image to break up this hard uniform line in a more organic way. So I can take my ramp output here, which is adding contrast to my actual texture image, and pipe that into the fall off of the occlusion. And now you'll see that I'm actually organically breaking up that edge based on this texture. And then from here, I can begin to increase the spread if I want to have a little bit more of a soft fall off here. It's going to bring in some of these areas. And then I can also adjust the kind of width or size of this effect by bringing up my max distance to affect a larger area. So this is a really great way to have a somewhat worn look, or if you have certain, if you have dirt collecting in these grooves, etc. And if I want to inverse that to get some sort of edge damage, I can always go back and invert the normal here and make any sort of adjustments that I see fit. I maybe bring down the max distance, and now you see that I've reversed that from the grooved areas to sort of the edge areas, and I've got some nice edge wear, which once again, you can also achieve these same effects with the curvature node. Again, one important thing to note is that this shader will take into account all geometry within the scene if you do not have this consider same object only checked. And we can see how this could be problematic if you have a piece of intersecting geometry. And as you see, if I have this cube intersecting my mesh, you're getting that occlusion effect around the cube. So if this was an animated piece and I had set up my shader, if any geometry got close or actually intersected, then you would get this almost flickering effect of the ambient occlusion going in and out around that object, or in areas where the object is very, very close to your particular mesh. Your options when it comes to correcting this issue is, again, turning on the consider same object only so that you're only affecting singular objects, in which case you would need to combine any sort of multifaceted model into a singular mesh. Or if you had only a single object which you didn't want to affect, you could actually go to your object, in this case the cube, right-click it, and add a Redshift object tag. Then within the attributes of the object tag, you could actually override the visibility, go down to the casts AO, and uncheckmark that, and now this object will not be generating any sort of ambient occlusion rays, and therefore will be ignored by the procedural shader. Now, this next node and its workflow is exclusive to Cinema4D. However, there's most likely something equivalent to this within other 3D software, and that is the Vertex Attribute node. Now, the Vertex Attribute node has multiple functionalities, but one of the most useful ways to use it is being able to take your weight maps and integrate them as dynamic masks within your shader network. So I'm going to go ahead and jump over to my viewport here. I'm going to go to the character menu and select the paint tool. And once I start painting on my sphere, I'm going to generate a weight map, which will be added as a tag to my sphere object. So let's go ahead and make a quick paint on this guy here. So I'm going to make sure I have my sphere selected first. And then I'm going to go ahead and just paint a nice little happy face here. And we'll see that map added here as a vertex map tag on our sphere object. So if I go ahead and select that and go to my attributes, I can give it a unique name. So I'll go ahead and say this is my happy face. Again, this could be named whatever you like. And then if I double click on this tag, I'll be able to re-access my paint tool options. And I'm not going to go into a lot of detail on here. I do recommend that you check out a video on more detailed information about this tool, but you can see that I can go back to my object, and if I set my mode to add, I can add additional detail here. I could set it to subtract and effectively erase that detail if I so choose. Scaling this up a bit, I'm going to go ahead and wipe that out. And if I set this to smooth, I could smooth out the edges of anything that I've painted by setting it to smooth and hitting apply all. Could increase the effect of the smooth, etc. So now if we go ahead and take a look at our shader graph, I'll go ahead and show you how we can use this weight map within our shader network. So if I select my vertex attribute node, and then I go over to my vertex map tag, and I hold down my left mouse button and drag that into the attribute name, and connect this to the output so we can see what we're getting, you'll see that our weight map has been translated into a black and white map, which we can use as a mask, or even just a texture within a color layer if we so choose within our network. So for a quick demonstration, I'm going to go ahead and pull in a color layer. I'm going to drop that guy into my network. I'm going to connect it to the diffuse color of my shader ball, or of my material. And then I'm going to go ahead and set a base color of red. And I'm going to set a secondary layer color of blue. So now if I view my material, we'll see that the layer 1 is overriding the red. So the entire ball is blue. But if I want to mask this blue out just within the vertex weight map, which I painted, you'll notice that you need to refresh your IPR quite a lot with this node. But if I go ahead and pipe this into the layer 1 mask of my material, we should just now be seeing the blue come up in these white areas of our mask. So let's go ahead and take a look at that. And right away, we can see that blue color and the diffuse coming through where we painted that smiley face on our weight map. And furthermore, I can add a ramp in between my vertex attribute and my mask input. And taking a quick look at that directly, I can actually adjust the contrast of that, as well as remap it with colors if I so choose. And then if I take a look at my final output, you'll see a much harsher transition here within that map. And so there's a couple of great things about being able to integrate these vertex weight maps within your shader network. One being that they do not rely on UVs, so you can paint anything that you'd like onto your models, and they do not need to be UV unwrapped in order to work. And the second great thing, if I go ahead and reconnect my output to the attribute node, if I select my tag here and go to its attributes and enable fields and go to the fields tab, you'll see that these weight maps now work with the R20 fields, so you can do all sorts of really interesting things like creating or adding noise, or creating animated maps, which you can use to very procedurally transition between two different textures or two different materials. The possibilities are endless when it comes to this new addition of fields in R20, so you can definitely utilize this to get some really, really cool results. And just as an extra tip, you can actually convert poly selections very easily and quickly into these vertex maps if you so choose. So I can go ahead and do that by selecting my sphere and going to the viewport here, making sure I'm set in faces mode. And then I can make a selection on the faces. We'll go and just do another face type smiley face selection. And then I can do a few things. I can go to select and set vertex weight, or save that as a selection for further selection. So let's go ahead and say I just set a selection at first, and that'll create a selection tag here. So in the case that, I have my sphere selected and I lost that selection, I could just double click on this to reselect it. And with that selected, I can go to select and set vertex weight. I'm going to go ahead and set that to 100 so that it sets a value of white in the selected areas. I'm going to hit OK. And you see we've created something very similar. Obviously, there's a little bit less of a fall off as when we hand painted it, as that was more dependent on our brush settings. And this will instead fill in the entire selection itself. But you can see I now have this new tag here, which I can go ahead and just rename that poly select so I remember what's going on here. And it still has that same fields functionality. And once again, I can go into my Redshift Vertex Attribute node and take this new map and replace it with the poly select. And you see that I've now successfully converted my poly selection into a usable vertex map, which I can plug into my vertex attribute and use it as a mask within my shader network. So next, let's take a look at the bump blender. So I have here this material, and I'm going to go ahead and just pipe in a bump map. Okay, I'm going to connect that here. Overall bump input. Take a quick look here at the result. So I'm getting some nice bump coming through here. It's pretty intense. So I'm going to go ahead and drop this down to say 0.1 and maybe exactly 0.05. And that's probably looking pretty good. I'm going to go ahead and set this to bucket mode so I can kind of see the final effect here. Okay. Now let's say that I want to combine multiple bump maps or blend multiple bump maps together. Now, I could take a series of black and white images, pipe them to a color layer, and get my overall bump map that way through a singular node. Or I could take multiple bump maps or multiple images that can be used as a bump map and use a bump blender to combine them. You can actually combine up to 4 different maps. But you can also, once again, take your final output of one bump blender, bump it, place it into another bump blender, and therefore daisy chain them to have an infinite amount if you so wished. So how this is going to work is I'm going to go ahead and take my first bump map, I'm going to pop it into the base input. You can think of this again as something very similar to the color layer, except now we're using bump maps. And now I can take the output of this and plug it into my bump input. And by default, since we only have one bump map here and it's the same exact one as we used before, we're going to get the same exact effect. So I can go ahead and take a snapshot of this for comparison purposes. And now I've got another, I've got a noise that I'd like to use as my secondary bump. So I'm going to go ahead and take a quick look at this in the output so I can kind of dial it in. Let's go and go to the coordinates. And we're going to go ahead and up this value, bring that scale down, and I'm going to go for like a pretty big noise to start. Maybe I'll increase the complexity a little bit. I'm going to go to the color, and I'm going to remap this, add a little bit of contrast. I'm going to bring the whites down and the blacks up. Okay, so now I've got some nice contrast going on here. I can use the bias to kind of shift it towards the darker values or the wider values if I so choose. And now I'm going to go ahead and pipe this into another bump map node. And I'm going to connect this bump map to my layer 0 bump input. Now, right away, and if I view my shader again, right away you're not going to see any sort of difference. And that's because our new bump input, or our second bump input, has a blend weight of 0. So if I bring this up to 1, we should be seeing it now. So now I have a very intense bump map right here, so I can go ahead and dial that back a little bit. Let's say 0.08. See how that looks. Okay, very subtle here. For intensive purposes of testing here, let's just have it a somewhat more visible value, say 0.15. Now we can kind of see how it's sort of breaking it up, very kind of bumpy. Complements this nice rock texture. But the one thing that's missing now is our original bump. So we could say, okay, maybe I want the blend weight to, if I lower that, it's like an opacity slider. Now I'm starting to bring back my original bump. But let's say that I actually want to composite them together so that I start with my original bump and I'm adding my noise on top of that. So I can set this blend weight back to 1, and if I activate additive mode, it's essentially going to first calculate the base bump, and then it's going to add the secondary bump on top of that. Okay? So now I can have multiple bumps and add them all on top of each other. So let's say I wanted a finer noise. Move these out of the way. If I duplicate this down, and I go ahead and, once again, directly connect my output to my noise. Say I go ahead and bring the scale up to, say, 50. Okay, so now I've got this very, very fine grain. And now I connect this bump output to my layer 1 bump input. And I go ahead and view my shader again. I'm going to bring the weight up. Temporarily, I'm going to turn off additive mode so I can just see what's going on with this fine grain bump. And you can see that's creating this very, very rough surface. So if I go ahead and recheck additive mode, you're now going to see all 3 of those bump maps added together, so they're all having an effect. And if I think that one is a little bit too intense and it's kind of overpowering the others, I can bring down this blend weight, and it's going to reduce the overall effect of that. Similarly, I could also just decrease the bump height scale if I so chose. But in this case, just for working purposes, bringing the blend weight down is going to have the same effect. Again, if I just want this particular bump map to show up in specific areas, I can also just put a black and white map into the blend weight as a mask. So, for example, let me go ahead and grab a black and white map here that we can use for this example. Okay, so I'm going to drag this guy in here. Take a look at this. Okay, and I'm going to go ahead and just copy one of these triplanars. So I'm projecting it. Going to replace the texture here. I've got this global scale controller, constant. Expand this a bit so it's easier to grab onto. I'm going to connect that to my scale of this guy here. Now we're going to go and view that. So we're going to use this as my mask. Once again, I can use a ramp to add some contrast to this so that I can have exact control over where this mask is going to reveal my bump and hide it. So I'll bring up the dark values so I get some really, really strong contrast here. Okay. And then I can go ahead and take this ramp output, pipe it into my layer 1 bump weight. And now anywhere that this white, 100% white is on my mask, the bump is going to show through at 100%. And anywhere it's black, it's going to be completely hidden, right? So I'm actually going to go ahead and make this a little bit more intense so we can really see how this is working. Okay, so now if I switch back over to my shader, connect that to the output, you can see that just in those areas, the white areas of my mask is where we see this really fine grainy bumps. So this offers you the ability to have complete control over where your bumps are happening and to combine multiple bumps to create some great variation within your shader. You can also combine normal maps using the bump blender. So if I take this normal map here, which take a quick look at. So I've got this normal map here. You can pipe it into a bump map node, and I'm going to just want to make sure that I change it from height field to tangent space normal so that it works with normals. And then I'm going to go ahead and connect it to my bump input 2. And I can turn off additive mode once I've set the blend weight to 1 to make sure that it's functioning correctly. And then if I set it to additive mode, now I have the ability to blend in any sort of normal map along with my other bump maps. Now, when it comes to displacement, it gets a little bit more complicated. So I'm going to go ahead and start by getting myself a displacement node. And I'm going to go ahead and take this displacement map, and I'm going to pipe that into the displacement node, texture. And now I'm going to connect this displacement node output into the actual shader output, not to my material, but to the shader output. And I'm going to set it as displacement. And now I've got that connected, but I am still not seeing any sort of displacement whatsoever. So I can check this here and make sure that actually texture is working. Okay, so that's there. So if I reconnect to my material, the next thing I'm going to need to do is actually go to my model in the objects menu here. I'm going to want to add a Redshift tag. I'm going to go to Redshift object. I'm going to select the tag, and I'm going to go to the attributes. I'm going to go to geometry, and I'm going to have to check some stuff on here. So you see that we've got some options for tessellation and displacement. Tessellation is going to allow the geometry to be subdivided to the point where we're able to see that detail from the displacement actually come through. And the displacement parameter is going to control the intensity and scale of that displacement. So I'm going to go ahead and turn this on. I'm going to start by turning on tessellation. Next, I'm going to go ahead and enable displacement. And now we should start seeing displacement occurring here in our render view. There it is. And I'm going to go ahead and save a snapshot of that for comparison here. The first thing I'm going to do is I'm going to disable auto bump mapping. Now, what auto bump mapping does is anywhere that the displacement is not viewed as necessary or it's unable to displace it, it's going to convert that into a bump map and then apply that over the top of the displacement. So if we pay attention here, as I disable it, go ahead and take another comparative snapshot and we can kind of see where that's occurring. So I'm going to go and let this process here. And now I'm going to save a snapshot. And switching between these two, you can kind of see these finer details coming through. So we've got these two options here. We've got displacement scale and maximum displacement. So displacement scale is going to act as a multiplier for our actual displacement node scale. So you see in my displacement node scale here, if I enter a value of 2, it's going to actually increase the effect of this displacement. And as you see here, I can go ahead and save a snapshot of that. Okay, I'm going to reset this back to 1. And now we're going to go back to our tag and change our scale to 2. And we should observe a very similar outcome. So these two are somewhat interchangeable, okay? So if I compare these two, you see that they're basically giving me the identical amount of displacement. All right, so I'm going to go ahead and reset this back to 1. We're going to jump over to the maximum displacement. Now, the maximum displacement, you can think of that as a maximum clamping limit for how much we can actually displace this. So since we're currently at 1, I might lower this down to 0.5 to make this a little bit more visible. Okay, so if I begin to raise my displacement scale, we know it's going to create a more intense effect, right? So let's go ahead and hike it up to 2. And again, we're getting a more intense displacement. So now let's go ahead and crank it up even further. So we technically should be able to enter any sort of number to this, and it will keep scaling this up to infinity, right? So I'll put in 100, and we'll give this a second here. And now what you're seeing is that all of a sudden it looks like nothing's happened except for the entire mesh has almost uniformly displaced outwards, and then it's stopped at a certain limit. And the reason for this is that the maximum displacement is cutting off that displacement. It's clamping it at a certain value. So in order to get some of that detail back, let's give this a more realistic number here. Let's say 5. Let's see what that looks like in the scale before we start tweaking our maximum displacement here. Okay, so you see that currently at a displacement scale of 5, we're still getting all of that displacement deal clamped and cut off, so it looks like it's almost a uniform displacement. So I'm going to start increasing the maximum displacement here. I'm going to bring it back to 1. And you're slowly going to see this detail come back, as well as having the actual displacement itself be allowed to expand further beyond this clamping point. So in here, we're starting to get this detail back. I'm going to go to bring this all the way up to 5. And this will probably be enough here. Okay, so now we're getting our full detail back, and none of it is being clamped off. So essentially, both of these work in unison. In order to have a specific amount of displacement, you need to make sure that your maximum displacement will allow that without clamping it. All right, so I'm going to go ahead and reset both of these to a value of 1. They're defaults, and let's dial in some displacement to a nice scale value that makes it really kind of apparent here. So let's bring this up to 2. And just to make sure that we're not clamping anything, let's bring this maximum displacement to, say, a value of 5, which again, this parameter is essentially just putting in place a maximum limitation that the displacement scale can actually reach. And now let's hop back up here to the tessellation and go through some of these settings. So we've got subdivision rules, got a few options here, or 2, Catmull-Clark with a loop or Catmull-Clark only. And in order to kind of observe this more thoroughly, let's go ahead and hop back over to our shader graph, and I'm going to connect a wireframe so that we can actually see the tessellation which is occurring here. And so we've got a few options here. We've got the subdivision rule. We have Catmull-Clark loop or Catmull-Clark only. And the main difference here is that you want to use Catmull-Clark loop for any mesh that is triangulated, while Catmull-Clark only is going to be more prone towards quads. In this case, we're not going to see a huge difference between choosing either option, although we are using quads. Next, we have screen space adaptive. And essentially what screen space adaptive does is it will subdivide the mesh based on its distance from the camera. So anything that's close to the camera will receive more subdivisions than anything that's further away from the camera. Because obviously, if you have objects that are far off in the distance, you're not going to be able to even see the level of tessellation detail on it anyway, so it's more of an optimization setting. So typically you want to keep this checked on. And then we've got the smooth subdivision. And to demonstrate exactly what's going on here, I'm going to go ahead and hide my shader ball temporarily and activate this low poly sphere. I'm also going to go into my wireframe here and show hidden edges so that we can see exactly what's going on. It's going to draw out the tries here. And I'm going to hop back here. I'm going to grab this Redshift tag that we set up originally, and I'm going to copy it over to my sphere. And I'm going to go ahead and turn off the displacement for now, so we just have the tessellation. And immediately, you can see that as soon as I uncheck smooth subdivision, rather than acting like a subdivision surface would or any sort of smoother, subdivision smoother in any sort of 3D program would, instead you're just tessellating the existing geometry and you're not smoothing out the actual shape of the sphere. So reactivating that, you can see that we're getting that nice rounded smoothing effect here, while also simultaneously adding the tessellation that we need. So this goes by a case-to-case basis. If you have a mesh that is not prepared to be smooth, then you'd want to make sure that you unchecked that smooth subdivision. Next, we have UV smoothing, and you have a few options here, where if you're noticing any sort of strange artifacting or stretching on the UVs of your mesh, as viewed through the textures on your model, you may want to try switching to a few of these to see if that corrects your issues. Next, we have the minimum edge length. And so in order to demonstrate exactly how these are going to work, I'm going to go ahead and re-enable displacement on this sphere. Okay, so now we're getting that nice rocky displacement here, and you can see it's pretty highly tessellated. So essentially what the minimum edge length is going to do is control the amount of accuracy when it comes to the detail within your displacement map. So if I set this to a higher number, let's go for 8, for example, you see that it's taking in less of that detail and only really paying attention to those large portions of the detail. And because of that large detail, it doesn't require nearly as much tessellation since it's ignoring the more fine details. Now, to get quite the opposite effect, if you want to really bring in that fine detail, you can set this to an even lower value. Let's go for a value of 0.5, for example. And you're going to see that the mesh becomes much more tessellated, but we're really starting to get that fine detail coming through. Now, in most cases, you don't want to set this too low because it's going to result in much, much longer render times, and re-enabling the auto bump mapping will help bring some of that detail back in without actually requiring you to tessellate the mesh to an extreme amount. So I'm going to go ahead and reset this back to the default of 4. And then our next option here is maximum subdivisions. So as you saw when we bring this down to a low number, we're getting a lot of tessellation here, But if we want to limit the amount of tessellation, we can either increase this number to have a higher maximum amount of tessellation before it stops itself. So if I set this to 8, you can see that now, although we have the same exact minimum edge length, we're allowing the mesh to be tessellated even further to bring out even finer detail. So if you're getting really, really up close on something, you probably will want to increase your maximum subdivisions if you're not getting the level of detail that you want. And likewise, if we lower this number, say to a value of 1, we're now limiting the amount of tessellation that it is allowed to make to try and get that level of detail dictated by the minimum edge length. So in this case, I might go for something around the default of 6, which would likely bring me enough detail for this particular distance from the camera, and then re-enable my auto bump mapping to get that fine detail that I might be missing. Next, we have the out of frustum tessellation factor, and essentially what this does is it controls the amount of tessellation on objects outside of the camera's view. So if we raise this number, any objects that have displacement and tessellation on them outside of the camera's view will be greatly reduced in terms of how many times they're subdivided. And bringing this value closer to 0 will keep that tessellation much more similar to if it was within the camera's view. Now, your initial reaction might be to crank this number up to a really high value, considering the benefits. However, you also need to keep in mind that any reflective objects that the camera is looking at will also reflect that low poly tessellation as well. And if there's any sort of camera movement, as that tessellation value increases as these objects come into frame, you could get some strange artifacting looking results within your reflections, as well as changing the way that lights and shadows are cast within your scene. So normally, you want to keep this at either default or just slightly inch it up to the point that you're not heavily impacting those variables within your scene. And if we drop down to the next option here, limit out of frustum tessellation, and enable that, it's going to give us this new option here to limit the maximum subdivisions for any objects affected by the frustum tessellation factor. So any of these objects outside of the camera's view that you are tessellating less than those within the view, if you want to set a maximum amount of times that they can be subdivided, then you would go ahead and enter that here, the same as if you were limiting the overall maximum subdivisions in the maximum subdivisions parameter. And so if we go ahead and turn off our sphere, bring back our shader ball, and reconnect it to our main shader here, I'm going to go ahead and refresh the IPR just to make sure that we get everything back properly. I'm going to go ahead and jump back into the tag here, and I'm going to go ahead and drop my minimum edge length to 1 and save a screen cap here. And then I'm going to go ahead and drop my maximum subdivisions to 0. And our ultimate goal here is to get the least amount of tessellation with the most amount of detail. So we obviously don't want to crank this too high and overly subdivide. The current shader ball that I'm using is already fairly subdivided within the model itself. So if you're working with a lower poly model, then you're obviously going to need to subdivide it more using the maximum subdivisions here, as well as having a fairly low edge length. So let's go ahead and start bringing this up. I'm going to jump it up by 2 to start, and then I'm going to compare. So I'm going to go ahead and let this process here, and I'm going to save another screen snapshot. And I'm going to look between these two, and I'm seeing very minimal difference here. For the most part, you can see in these specific areas here, you're starting to see some of that higher detail come through, which was at the default of 6. Okay, so I'm going to go ahead and bring this up another 2. So now we're at a value of 4 max subdivisions. And we're going to look at these areas once more. And now we're seeing some of that detail. And compared to the original at 6, I'm not seeing very much difference whatsoever. So I'm going to go ahead and say that 4 is plenty of subdivisions for this particular model. Of course, if we're zooming up really close, then we would definitely need to bring this max subdivision value higher to compensate for that. But if this is about as close as we're going to get, then this is working just fine. And then I can go ahead and turn my auto bump mapping back on to get any of that really fine detail back into my render by converting it to a bump map. So I'm going to go ahead and let that go. And then I'm going to take a snapshot here just so we can toggle through these guys. And if we look back at our original tessellation here, obviously we're seeing a lot more of that detail by enabling auto bump mapping, but we were able to dial in the correct amount of displacement in the first place without getting ourselves confused as to what was actually being displaced and what was an additive bump map. We can also combine multiple displacement maps in the same manner as bump maps by using the Displacement Blender. So I'm going to go ahead and drop Displacement Blender in here. And you'll see that it has very similar parameters to the bump map displacer, or blender. And I'm going to go ahead and pipe in my first displacement map here into the base input and connect my output to the displacement in the shader output. And we're not going to see any differences here because we are still using our original displacement. But if I copy this displacement node here and I connect it to my layer 0 as the input, and this time I use a noise and I pipe that into my texture, we can take a look at our noise really quickly here. And we'll give it a second to process that in the IPR. I'm actually going to go ahead and switch off bucket for the moment. And of course, anything that is black is going to be pushed into the mesh, and anything that is white is going to be expanded outwards. So I'm going to go ahead and take a look, reconnect here to my material. And I'm going to go to my displacement blender, and I'm going to crank up my blend weight to 1. And we'll give it a minute to process here. Okay, so now I'm seeing some extreme displacement here, so I can bring down the scale of my noise and bring it down to, say, 0.2. And we'll see what's going on here. Okay, but one issue that we're seeing now is it looks like we're overriding our original displacement, and we've completely replaced it with this noise. And once again, in order to layer these on top of each other, we can, so that they're both influencing the displacement, we can check on additive mode. And we will see that the original displacement is showing up, and then our noise displacement is being added on top of it. And once again, you can daisy chain these displacement blenders to have an infinite number of mixed displacements. And in the case that we only want certain displacements to show up on specific parts of the mesh, we can go ahead and use any sort of mask that we've generated. So in this case, if I replace my second displacement layer here with a finer noise, go ahead and give that a minute to load up. I'm going to go ahead and dial this back a little bit so it's not so crazy. 0.05. I can use this other noise, which is essentially a black and white image, to influence where this very fine noise displacement will actually show up. So if I really quickly take a look at this noise that I'm going to use for the mask, you can see that I've got these dark areas and I've got these light areas. So I'm going to go ahead and actually scale this down slightly so that it's larger. And we've got more distinguishable areas. I'm going to go ahead and hop in really quick to the remap here, and I'm going to bring up the dark values so that we get a little bit more empty pockets here, so we can clearly see where our fine displacement is coming through. And then I'm going to go ahead and pipe that into the displacement weight of our very fine displacement. And now I'm going to switch back to our material, give it a second to process. And now if we zoom in here on our mesh, you can see that that fine displacement is only coming in where we've dictated it using our black and white noise mask. Now, in order to create more complex shaders made up of multiple materials and layers, I'm going to want to use the Material Blender. So I'm going to go ahead and grab that and drag it into the shader graph and expand this guy so we can see what's going on here. And right away, taking a look at the UI, you're going to see that it looks very familiar to the color layer. Except rather than using images, we're going to be using actual materials. So I've got two materials present in my scene. I've got this rocky material as well as a shiny red plastic material. So I'm going to go ahead and start by connecting my red plastic to the base material of my blender. And then I'm going to go ahead and connect my blender to the output so we can go ahead and take a look at what's happening here. And right away we see that nothing's changed. We're still looking at our red base plastic. So in order to blend our materials, we're going to need to add our secondary material. And I'm going to go ahead and connect that to my layer 1 color. And we're still not seeing anything happening here. And that's because our blend color is acting the same way as an opacity. So since our blend color is black, that means that our blend amount is 0. So as I increase this towards white, go ahead and set it to 50% first, you're going to see this secondary material blending with our plastic, the rocky material blending with the plastic material at 50%, and you're starting to see that come through. And as I bring it up to full white, you're going to see that rocky material completely override that plastic material. So similarly to how we were using the masks in other facets of our network, I've got this mask here, which is combining a curvature map with some noise breaking up the curvature effect there, as well as a base black and white kind of grungy texture. And I'm combining those by adding my curvature map over the top, meaning that anything that is white will be added and anything that is black will not. So as you see, I'm bringing in these white areas from my curvature on top and combining them into a more interesting mask. And from here, I can go back to my material blender, take a look here, and I can go ahead and replace my blend color from white using this mask that I've generated and plugging that into the layer 1 blend color. So now anywhere that it's 100% white on my mask, you're going to see that layer 1 show through, which is the rocky material. And we can see that here. If I go ahead and enable my bucket mode, you can see that we're now starting to get a nice blend between both the rocky texture and the red plastic. And I can control my mask, of course, using my color remap nodes or my remap nodes. In this case, I'm using a ramp. So I can go ahead and maybe bring in the rocky texture a little bit more by expanding the white areas of my map. And now you see we're getting almost a very dirty plastic going on here. I can increase the radius on my curvature to maybe thicken up that effect in the grooves. So perhaps I'll set it to a value of 0.4 and see what that gives us. And once again, if I'm not entirely sure what's happening in my mask, I can always reconnect that to my output so I can directly see what's going on. Okay, and maybe I want to clamp these black values a little bit harder and instead bring the white values in. Now, when it comes to displacement, we're going to go ahead and call back the Displacement Blender and drop that guy in. And just as before, we're going to use it to combine the different displacements that we've created per material. So I've got my plastic displacement here, and I'm going to go ahead and drag it in and pipe that into my base displace. And then I'm going to take my rocky displacement, and I'm going to put that into layer 0. And rather than use additive mode in this case, because I want each of these displacements to only occur for the correct material, I'm going to go ahead and leave additive checked off. And I'm going to take our mask, which we're using to blend our materials, and use that same mask to control the blending of our displacements. I go ahead and connect my mask here to the displacement weight. And once again, wherever the mask is white is where our displacement will occur. And because we're influencing, using that same mask to influence where the material shows up, we're going to create a relationship between where the material shows up and where the displacement occurs. I'm going to go ahead and drag this guy into the displacement of my shader output. And I'm going to go ahead and activate my displacement in the Redshift object tag by turning it on, making sure my tessellation is enabled as well as my displacement, and all my settings are dialed in. And now we can see that we're getting displacement here on our mesh, except there's one big problem, and that's that our secondary rock displacement appears to be completely overriding our plastic displacement. We can see exactly what the displacement on our plastic looks like by connecting that to our displacement input here and viewing that individually. Give it a second here to update. And as you can see, our plastics displacement is this very, very low intensity noise, while our rocky displacement, if I connect that directly, is going to give us the same result as we were seeing previously, even though we had this mask piped into the weight, which should only be creating this more intense displacement on the rocky areas that we've masked out. Because the curvature is calculated after displacement, it's interpreting this layer add here in our mask as being a solid white, and therefore it's overriding our base material because of the fact that the rocky displacement is coming through at 100%. So in order to work around this, I'm going to go ahead and take my original texture here without the curvature being blended over the top of it, and I'm going to directly pipe that into the displacement weight and make sure that's all connected. And now we should be seeing the displacement occurring in a more predictable fashion here. And as we can see, it's pretty intense, so I'm going to go ahead and lower the scale of the rocky displacement down to something like 0.25 so that it feels a little bit more natural and less insane. And as this process is here, you can see now we're getting that nice kind of rocky displacement on top of our plastic. Additionally, there's this option here on each layer called additive. And what that's going to allow us to do is if I go ahead and create a new material to blend in here, I can take this material and plug it in to the layer 2 color. And I can just give it, let's say, a bright blue. Jump back into my material blender. And let's go and set the blend color to white so that we're completely overriding the other two materials with just this solid blue. With a little bit of reflectivity. It's going to be somewhat plasticky, highly reflective. And now if I turn on additive mode, you're going to see a few strange things occur. So first of all, the blue diffuse color is being added over the diffuse color of the other two materials, similarly to the effect you would get if you used a blend mode in something like the color layer. The other thing that's happening is our reflection is also being added to the reflections of the other two materials as well. In most cases, you'll end up using this additive blend mode to stack additional layers of reflectivity onto certain materials such as a metal or a hardwood floor that has some sort of finished coat on the top. So in this case, I have a dull copper material, and I can go ahead and set my blend color for my secondary material to white. And I've got this kind of gray plastic material. I'll set that to additive mode, jump into the material, and get rid of the diffuse component. So now I'm just working with this reflective layer, and right away you can see it looks like it has some sort of sheen to it, as if there's some additional coating on top of the metal itself. And from here you can add textures into things like the roughness or bump, as well as mask the overall effect of this reflective additive top coat. So once again, I'd like to say thanks for watching, and go ahead and stay tuned for the next tutorial where I'll be showing you how I utilized all of these nodes to create this procedural texture-based frost shader, which you can find a free download link to in the comments section below.